Okay, Professor Jim Schultz here from my Finance 680 students. I wanted to go ahead and shoot this video for number 49 in Chapter 6. As you can see, I already have my solution pulled up for this problem. And so let's go ahead and get right to work. Let's work through how to set this problem up and how to solve it. And so the key to this problem, obviously, is at least at the beginning, is understanding what is being asked of you. And the critical element or elements there is going to be in the question of the problem, which reads, how much money would you need to invest in B today for it to be worth as much as investment A 13 years from now? Put another way, you need the present value of B, so the amount required to invest in B today, to be equal to the future value of A. Right? That's how to mathematically translate the question of this problem. And so that's critical. If you can't do that, then you're going to have a really difficult time solving this problem, obviously. So once you can do that, then when you look at both investment streams, you look at both investment options A and B, you can see that, okay, finding the future value of A is pretty simple, right? It's just going to be a classic time value money setup where you're solving for the future value of this annuity, the present value is 0, it's a $1,500 payment, and then I and N have to be monthly, right? And so you make those adjustments, and then you come out with $394,352.43, right? So that's pretty straightforward, all right? Now, when you turn over to B, you see that the problem says, I'm looking at it now, you have your choice of two investments. Investment B is a 7% continuously compounded investment. All right, so I chose this problem to get you guys familiar with continuous compounding. All right, you've seen this formula. This formula we put up in class a lot. I've referenced it many times. This formula is when you have discrete compounding, which in layman's terms just means something is compounded a finite number of times, like daily or monthly or weekly. In other words, you can count the number of times that it's compounded. This is going to be your traditional usage of a time value of money problem. But if you have continuous compounding, what that means is it's literally compounded an infinite number of times. Or in other words, it is always compounding, right? So if it is always compounding, this formula changes to this formula. All right, it's no longer PV equals future value divided by 1 plus I raised to the n. It's PV equals FV multiplied by e to the negative I times n. That's your e to the x key. That's going to be on your calculator. That's how you handle infinite compounding or continuous compounding. And so once you understand this, it's not too bad, right? PV equals FV times e to the negative I minus n, which is just another, a negative exponent is another way of saying that this would be in the denominator like this is in the denominator. And so the only thing that's critical about this exponent is your I and your n must be annual, even if the problem says monthly payments or whatever, because now it doesn't really matter anymore. The frequencies aren't important because you now have continuous compounding, right? And so in this problem, your I was, let's see, for B, the I was 7%. So this is 0.07 times an N of 13. So that's how you get 0.91. And then if you literally take 394,352.43 e to the x and then negative 0.91, this is your answer. This is the present value of B that is required to get to the future value of A.